Hello everyone. Today we are going to discuss about the BEEE lab viva questions for part B experiments. In the part B experiments, we have the experiments like Pn-junction diode and the GNR diode and half-wave rectifier and full-wave rectifier and common base configuration and common emitter configuration. These are the experiments we are having in the part B BEEE lab. So for these experiments, we will discuss some viva questions. So in the first question is, what is diode? A diode is a two-terminal electronic component that conducts electricity primarily only in the one direction. Okay, which allows the current only in one direction is called as a diode. Diode is basically a switch, okay, which allows the current only in forward bias. In reverse bias, the diode will be in the off condition. If you see the diode symbol, this is a symbol of the diode, okay, which is having the anode and cathode. It is a P terminal and it is a N terminal. Next, to define cut-in voltage of the diode and specify the values for the silicon and germanium diodes. The forward voltage at which the current through the junction starts increasing is called as a cut-in voltage. Okay, the voltage where the diode starts conducting is called as a cut-in voltage. Cut-in voltage for silicon is denoted by V gamma. Cut-in voltage for silicon is 0.7 volts. While in case of germanium, the cut-in voltage is 0.3 volts. Next question is, what are the applications of Pn-junction diode? So Pn-junction diode we have used in some applications like rectifiers and the clamping circuits and the clipping circuits and the digital logic circuits. And these are some applications. And also we use in voltage multipliers and etc. These are the applications of the Pn-junction diode. Next one is, draw the ideal characteristics of Pn-junction diode. So this is the ideal diode when the diode is in forward bias condition. This is a forward bias condition. Positive terminal is connected to P, negative terminal is connected to N. Then the diode will be in the forward bias condition. In forward bias condition, ideal diode is replaced by closed switch. Now, if we apply the reverse bias condition, if we reverse the terminals like this, negative terminal, positive terminal, negative is connected to P, positive is connected to N. In this case, the diode will be replaced with the open switch in ideal diode. Next, what is knee point? The forward voltage at which the current through the junction starts increasing rapidly is called as the knee point. Okay, up to a certain point, the diode starts increasing slowly. After this knee point, the current increasing exponentially, that is rapidly, is called as a knee point. Next, diode current equation. Diode current equation, I is equal to I naught into e power q into v divided by eta into kt minus 1. Here, I naught is called as a reverse saturation current, q is the charge and v is the voltage, and eta is called as the ideality factor, and k is the Boltzmann's constant, T is the temperature. This is the diode current equation. Just you have to write the diode current equation in this if they ask what is diode current equation. Next, forward and reverse bias. Here, in forward bias voltage, positive terminal of the supply is given to the P type and negative terminal of the supply is given to the N type. Then the diode is said to be in the forward bias condition. In the forward bias, positive terminal is connected to P and negative terminal is connected to N. Then we can say that diode will be in the forward bias condition. First of all, biasing means giving the external supply to the any electronic device is called as a biasing. If we give the supply like this, it is the diode will be in the forward bias condition. Suppose if we interchange the terminals, like negative terminal is connected to P and the positive terminal is connected to N, then the diode will be in the reverse bias condition. This is about forward bias and the reverse bias. Next, what is reverse breakdown voltage? It is the reverse voltage at which the breakdown of the junction takes place and the reverse current increases rapidly is called as a reverse breakdown voltage. This reverse breakdown voltage occurs in the reverse bias of the PN junction diode. Next, why the GNR diode acts as a voltage regulator? The GNR diode can generate the constant output voltage in the reverse bias with the variation in the input voltage and the load resistance. Hence, the GNR diode acts as a voltage regulator. In reverse bias, up to certain voltage, the current increasing slowly. After 4.7, around 4.8 volts, the diode, GNR diode reverse voltage is almost constant, but there is a change in the current here. Current increasing, but there is no change in the output voltage. Output voltage is constant. Hence, GNR diode acts as a voltage regulator in the reverse bias condition. What is line regulation? So this is the GNR diode regulation diagram. In the line regulation, input voltage is variable, but the load resistance is constant. Okay, in this case, the output voltage should be constant. That is called as a line regulation. In line regulation, supply voltage is variable, but the load resistance RL is constant. This is called as a line regulation. But in case of the load regulation, this is the regulation diagram. In this, Vs is constant, but we will vary the load resistance by using decayed resistance box. In this case, if the load is variable and the Vs is constant, the output voltage we should get constant. That is called as a load regulation. Here, supply voltage Vs is equal to, we will get constant, but RL, load resistance, is variable. Okay, in both the cases, if the input is variable or output is variable, but the output we will get constant. That's why we are using GNR diode as a voltage regulator. In which region GNR diode can be used as a regulator? In the reverse bias condition, after reaching to this voltage, okay, here current is increasing continuously, but there is no change in the voltage here. Voltage is constant. That's why in the reverse bias condition, GNR diode acts as a regulator, that is voltage regulator. Next one is, what is rectifier? Rectifier is an electronic circuit which can convert AC into the pulsating DC. It converts AC to pulsating DC, not pure DC. Pulsating DC is nothing but it is having the DC plus AC ripples. Okay, if you see the input here, input is AC. If we give the input AC to the rectifier circuit, we are getting the pulsating DCs like that. We will not get pure DC at the output of the rectifier. This is a pulsating DC. Pulsating DC means DC plus AC ripples. Next, what is ripple factor? A ripple factor is defined as the ratio of RMS value of the AC component to the DC component. The ripple factor functionality is to explain how much amount of AC ripples present along with the DC output. See here it is looking like AC, but we will not call it as AC. This is called as a pulsating DC. This is the input of the rectifier. It is output of the rectifier. Even it is pulsating DC, but it is looking like AC only. That's why it is having the AC ripples. Pulsating DC means first of all it is a DC plus it is having the AC ripples. That how much amount of AC ripples present in the output of the DC, that we will find out by using this ripple factor. This ripple factor is denoted by gamma, that is VAC divided by VDC. We can also write the formula we are having, that is VRMS whole square by V average whole square minus 1. Next one, ripple factor of half-wave rectifier is 1.21 we will get. Next, define peak inverse voltage. This is the maximum value of the reverse voltage which the rectifier has to withstand during the non-conduction period. Okay, in the reverse bias condition, diode will not conduct. Diode will be in the open circuit, or diode will be in the open circuit condition. In the open circuit condition, the maximum voltage appears across the reverse bias condition. That voltage at the non-conduction period is called as a peak inverse voltage. Okay, the peak inverse voltage of the half wave rectifier is the peak inverse voltage. Simply we will call it as PIV. The peak inverse voltage of the half wave rectifier is, we have VM. This is the peak inverse voltage of the half wave rectifier is VM. Next, define efficiency. Rectifier efficiency is the ratio of DC output DC power to the input DC power. The efficiency is denoted by eta. That is a power output at DC divided by power output at AC into 100. This is a formula for efficiency. So what is the efficiency of the half wave rectifier? The efficiency of the half wave rectifier is only 40%. Next, in case of full wave rectifier, we will discuss. Before that, what is transformer utilization factor? Simply TUF. The transformer utilization factor of a rectifier circuit is defined as the ratio of DC power available at the load resistor to the AC rating of the secondary coil of the transformer. This is called as a transformer utilization factor. DC power output to the and AC power at the secondary coil of the transformer. Next one is what is the transformer utilization factor of half wave rectifier? Transformer utilization factor TUF of half wave rectifier is only 40%. Next, what is the peak inverse voltage of full wave rectifier? We discussed already peak inverse voltage of half wave rectifier, we got VM. But in case of peak inverse voltage of full wave rectifier, we will get 2 VM. The peak inverse voltage here, peak inverse voltage is 2 VM for the center tapped full wave rectifier here. Center tapped full wave rectifier. This is. While in case of bridge full wave rectifier, the peak inverse voltage is VM. Okay, that is the advantage of the bridge rectifier. This is the disadvantage of the center tapped full wave rectifier. Generally, peak inverse voltage should be VM only. Next, what is the efficiency of full wave rectifier? We got efficiency of half wave rectifier is 40% we got, while in case of the full wave rectifier efficiency is 81%. What is the transformer utilization factor of full wave rectifier? In half wave rectifier we got 40%, while in case of the full wave rectifier transformer utilization factor we will get 81%. Next, ripple factor of full wave rectifier. Ripple factor of full wave rectifier is 0.48. In case of half wave rectifier, we got 1.21. The ripple factor formula is equal to Vrms whole square divided by V average whole square minus 1. So this is the ripple factor formula. It is denoted by gamma. The ripple factor of full wave rectifier is 0.48. Next, what is the difference between half wave rectifier and the full wave rectifier? The most significant difference between the two is that half wave rectifier converts only half cycle of AC into DC, whereas the full wave rectifier converts complete cycle of the AC into the DC. Okay, here in half wave rectifier only positive half cycle is converted into the output, but in case of the full wave rectifier both positive half cycle as well as the negative half cycle, only positive half cycle, only one cycle is converted into the output. But in case of full wave rectifier, both positive half cycle and the negative half cycle both will convert it into the output. And there are many differences. In half wave rectifier only we use only one diode. In case of center tapped full wave rectifier we use 2 diodes, and in case of bridge rectifier we use 4 diodes. In half wave rectifier we will get the efficiency is only 40%. In full wave rectifier we will get the efficiency is 81%. Okay, so we can tell the many differences here. These are some differences. What are the applications of rectifier? This rectifiers used to convert main AC to DC. In mobile chargers we use rectifiers. And in the laptop adapter, we use rectifiers. In laptop adapter also require DC. To convert AC to DC, we use rectifier. And the RPS and the other electronic component, we use rectifiers. Next, V average value of the half-wave rectifier and the full-wave rectifier value. The V average value of the half-wave rectifier is Bm by pi. While in case of the full-wave rectifier, it is 2Vm by pi. This is for half-wave rectifier and it is for full-wave rectifier. Next one is VRMS value of half-wave rectifier and the full-wave rectifier. The VRMS value of half-wave rectifier is Vm by 2. While in case of full-wave rectifier, it is Vm by root 2. This is the VRMS value of half-wave rectifier and the full-wave rectifier. Next, what is the necessity of the transformer in the rectifier circuit? In rectifier circuit, one of the component is transformer. What is the use of this transformer? Transformer is an electrical machine which transfer the electrical energy from one circuit to other circuit is called as a transformer. Transformer is having the two windings, that is the primary winding and the secondary winding. If the secondary windings are less compared to primary winding, it is called as a step-down transformer. In the rectifier circuit, we use step-down transformer to decrease the voltage because the DC levels of the transformer, the DC levels are very low. That's why we have to decrease the voltage by using step-down transformer. This is about the transformer in the rectifier circuit. Next, what is the necessity of the diode in the rectifier circuit? The one of the component we are using in the rectifier circuit is diode. The diode is a semiconductor device which allows the current only in one direction. It is used for the switching purpose in the rectifier. In the diode, it allows current only in the forward bias. It does not allow in the reverse bias condition. That's why it is used for the switching purpose in the rectifier circuit. Next here, what is transistor? Transistor is a semiconductor device which can transfer the signal from one resistance region to the other resistance region. That is, transfer the weak signal from low resistance circuit to the high resistance circuit. Simply, the transistor transfer the signal from one resistance region to the other resistance region. That is, weak signal is converted into the strong signal. And that's why transistor used as an amplifier. What is the three configurations of the transistor? Transistor is having three configurations, that is common emitter configuration, common base configuration, common collector configuration. These are the three configurations the transistor is having based on the terminal is connected to ground. What are the three regions in the transistor? There are three regions transistor out in the output stage. The transistor is having three regions. First one is an active region. Second one is a saturation region. And the third one is a cutoff region. These are the three regions we are having at the transistor output characteristics. First one is what is active region. So before that, we will discuss what is saturation region. So it is a NPN transistor. In NPN transistor, it is having the two junctions, three terminals, emitter, base, and the collector are the three terminals. It is having the two junctions. It is an emitter junction. It is a collector junction. In this emitter junction, here we can call it as emitter junction is forward bias, and collector junction, that is JC, is also forward bias. As a forward bias of the both the junctions, the transistor acts as an on switch. Due to the forward bias of the both the junctions, more amount of forward current flowing in the transistor. In this junction, resistance is very low, so that we will get the on switch in the transistor. That's why transistor acts as an on switch in the saturation region. In case of the cutoff region, in the cutoff region also, we will take NPN transistor only. It is emitter, base, and collector terminal. It is a two junctions. It is a emitter junction and it is a collector junction. In cutoff region, emitter junction is reverse bias and the collector junction is also reverse bias condition. As the reverse bias of the both the junction, the transistor acts as an off switch. Due to the reverse bias of the both the junction, the current flowing is very low because it is in reverse bias. The current flows is negligible. The resistance offered in this region is very high. That's why in cutoff region, transistor acts as off switch. Next, in active region, it is a emitter junction, it is a base junction, it is a collector junction, sorry, terminal. It is a emitter junction and it is a collector junction. In the emitter junction, we can take forward bias, and in the collector junction, it acts as a reverse bias condition. We will connect in the reverse bias condition in active region. In one is forward bias and one is the reverse bias. Due to the forward bias of the emitter junction, the current flows in the emitter junction is very high. Due to the reverse bias of the collector junction, the current flows in the collector junction is very low. It is forward bias, that's why it is very high. It is reverse bias, that's why it is very low. In active region, transistor acts as amplifier. Amplifier means increase the strength of the input signal is called as amplifier. In active region only, transistor acts as amplifier. In which region transistor acts as amplifier? In active region. The answer is active region. If they ask this question, you have to say in active region, transistor acts as amplifier. What is active region means? You have to explain all these things. Why the transistor is called as current control device? If the output current equation in terms of gain and the input current and IC naught is given by output current is equal to gain into input current plus 1 plus gain into reverse saturation current. Here IC naught is called as a reverse saturation current. Here if you take the common emitter configuration, in common emitter configuration, output current is indicated by IC and gain of the common emitter is denoted by beta and the input current is denoted by IB plus 1 plus beta into IC naught. Okay, from the equation we can say that there is no voltage term here. This output current is depends on the input current. Okay, this output current IC depends on the input current IB. Hence, BJT is a current control device. This output current we can control by using this input current. Okay, that's why it is called as a current control device. What is the relation between alpha and beta? Okay, alpha is nothing but the gain of the common base configuration and beta is nothing but the gain of the common emitter configuration. If you see the relation, alpha is equal to beta by 1 plus beta and beta is equal to alpha by 1 minus alpha. These are the relations we are having for alpha and beta. Define current gain in the common emitter and common base configuration. See here, generally the gain is denoted by output quantity divided by input quantity. That is called as a gain. Okay, suppose if you want the current gain of common emitter is denoted by alpha. Sorry, common base. For common base, so we will take common base here. The current gain of common base, first common base is denoted by alpha. Alpha is equal to the output current of the common base is denoted by IC and input current is denoted by IE. IC by IE is nothing but the current gain of common base configuration, which is denoted by alpha, current gain. Next, in case of common emitter configuration, the gain is denoted by beta. The output current of the common emitter configuration is IC. Input current is IB. Current gain beta is equal to IC by IB. Next, draw the NPN and PNP transistors. And this is the NPN transistor, which is having the three terminals, emitter, base, and the collector. And if you see the symbol here, this is the emitter terminal, and it is a base terminal, and it is a collector terminal. In NPN transistor, emitter current direction is outside, and the remaining current directions are inside. In case of PNP transistor, which is having the three terminals, emitter, base, and the collector, and it is a symbol of the PNP transistor. In PNP transistor, emitter current direction is inside, and the remaining currents are base current and the collector currents are outside. It should satisfy I is equal to IB plus IC equation. These are the symbols of the PNP and NPN transistors. Next, what is bipolar transistor? The bipolar transistor is a semiconductor device in which the electric current flows due to the both holes as well as electrons. The examples of the transistor is BJT. That is examples of the BJT is bipolar junction transistor. Okay. Next one is, what is unipolar transistor? The unipolar transistor is a type of transistor in which the current flows due to only one type of charge carrier, that is either electron or holes. But in case of bipolar transistor, the current flows due to both holes as well as electrons. The examples of the unipolar transistor is unijunction transistor or FET. FET is nothing but field effect transistor. Next one is, what is amplifier? The amplifier is an electronic device that is used to increase the power level of the input signal is known as an amplifier. The transistor acts as an amplifier in the active region. Simply increasing the signal strength is called as an amplifier. Okay, these are the some viva questions of the part B experiments. So all of you go through the short answer questions with answers that we already uploaded that video. So please go through that short answer questions videos and this lab viva question. Then you can able to answer all the questions in the lab exam.